What's that sound? It's the desk of Ladyada.
Beep, beep.
What's going on?
Hey, it's Friday night. We're hanging out at my desk. It's the electronic crib. We've got all sorts of sensors going on. I thought we would just do a little stream.
Let's do this.
Okay, well, it's IR Sensor Week here at the desk.
It's also National Robotics Week.
It's also National Robotics Week, which robotics uses sensors. Oh, wait, I should get my whiteboard thingy. Hold on.
Okay. It's gone.
No, I'm back.
So last time I saw her, she went to get a pack of smokes.
Yes.
Oh, you're back.
Okay, LED smokes. Okay, so we used this whiteboard diagram. We were talking about IR sensors and LEDs, and we're talking about how they're just wonderful little devices and you can use them for all sorts of things. For example, we've been showing how to use remote control and then detect that with an IR sensor receiver, and also how to send IR data from our CircuitPlayground Express, the circuit board we're working on. You got the emitter, you got the receiver, you can emit data codes, like we talked about IRDA or remote control, but I also mentioned at the very beginning that another really useful thing you can do with IR sensors and receivers is use them as proximity sensors or break beam sensors. So for example, this is an integrated sensor. This is the VCNL 4010, which is a sensor by, I don't know who makes this, Sharp? No, I don't remember. Whoever makes it, I can't remember.
Let's move the window over.
I'll move the window over.
Oh, very good.
And this sensor, this little thing in the center here, you can barely see it, but in the center here is two dark spots. That's where the IR transmitter and receiver are. And if you looked at the data sheet, hold on. It's so big. It's by Vishay. Yeah, Vishay loves this stuff. So you actually see here like these bumps. This is the transmitter and receiver. And this basically has an IR LED. Actually, it's an ambient LED as well, but has a IR LED, and then it has a IR receiver LED, and it basically bounces light off of objects, and it can detect how far away they are. You know, it doesn't work from huge distances, but it does work pretty well. One of the things that these are often used for is phones, so that when you hold your phone up to your face is very capacitive. We talked about capacitive touch. That way your face doesn't press the buttons, right? That's how it turns off, how it knows to turn off when you hold up to your face. It's doing a proximity sense when your face is near. So we have these sensors and they do proximity sensing. So this one does about 1 to 15 centimeters. Actually pretty good. 10 to 150 millimeters. It's just pretty good. It's like 8 inches-ish. But this is a super tuned, specifically designed sensor. We also have those IR break beam sensors I mentioned. And these kind of a different idea. You transmit IR and then you receive it. And it's invisible to human eyes, and so you can have IR break beams in dark rooms, or in light rooms nobody really notices, or you can, it's basically you can't detect it unless you have a camera that doesn't have an IR filter. So we've actually been designing the CircuitPlayground to have IR transmit and receive using a detector and emitter for data codes, so like doing remote control. But I thought what would be really neat is if I could somehow hack in the ability to also do some basic proximity sensing, or maybe even break beam sensing if you have two of them. But proximity sensing I thought would be kind of neat, something where you can do basic, hand detection, or if something is moving in front. And so what I did in the design, let's look at the area for the sensor. So this is the sensor that we talked about, and to most IR receivers, I'll show what they look like. They look like this. They're through a hole, and they're totally integrated. They have the IR detector inside as well as a chip, and it just sends out the codes. The way I'm doing it to basically save space, and because I want to be fully surface mount, is I have the IR receiver diode and a IR preamp that's basically a device that biases and listens to the signal coming out of this diode and then does the decoding. It's basically a two-part solution. You have the LED, the diode detector, and the decoder separated. It's actually about the same price as having an integrated one. You just have two components, which isn't too bad. But one of the nice benefits of this is you can listen in on the raw data from the IR LED detector here, the detector. So instead of just having it go straight in, I actually tied this pin. Hold on. This is the, hold on. There's no real way to scroll. There you go. The IR LED here, this LED is the receiver, and it goes into the sensor, which is this chip over here, but I also take that and connect it to an analog input on the microcontroller because I want to be able to read that raw data. Now again, it's not tuned specifically for this use. This is not going to be super perfect, but it might be good enough. So then in my code, and my prototype actually didn't do this. I actually have this, I'm just using a blue wire. But in my code, what I'm going to do is I basically set up the transmission pin, and I set up the receiver pin. And instead of transmitting IR codes, I'm just going to pulse the LED high for about 10 microseconds, long enough to make sure that the receiver half gets it. And then I'm going to do an analog read on that proximity pin. So if you look here, basically turn this LED on, really bright. Remember, it's 350 milliamps going through this LED, but only for a split second, and then read from this LED, which is nearby. One of the tricks is that this is a very narrow beam LED. I got LED with a lens, so it's only 20-degree beam spread, so it doesn't leak so much over here. It's pretty good at directing it only up. So it should only bounce off of my hand, for example. So let's look at this code. We'll upload this code to my CircuitPlayground, and we can go to the overhead. I'll just point out the parts here.
I have an infrared story when we're done.
Okay. All right, so I'm just uploading the code. Code is uploaded. Okay, so here is the IR LED. Now, it is pulsing, but it's just, sorry, if I open up the serial console, it'll start pulsing. You can see it's pulsing very, very quickly. It's flickering. You can see the flicker. And then this is the receiver. So what I'm going to do is I wired a little, I soldered a little blue wire here so I can look at this on the oscilloscope. So.
Oscilloscope cam?
No, not yet. I'm going to probe on there. So you got one probe looking at the output of the LED. This way I can, basically it's my sync, so I can see where I'm starting. And then over here, I will take the other probe and I will clip onto the cathode of the IR detector. Remember, this is going into the detector chip. I'm grabbing that signal right before it goes to the detector chip. And then now I can go to the oscilloscope cam.
Okay.
Okay, so over here, this yellow pulse, that's the LED. And that's going down because this LED is, the anode is connected to 3.3 volts, and then I'm pulling it down to turn it on, because that's, it's a little bit more effective to turn LED on with an N channel or NPN than a P channel. So you pull it down, so it gets pulled down. And this blue line here is the detector diode. So you can see that there is a little bit of detection. Now there's going to be a little bit of leakage again. There's no clear divider. There's no divider between the two. So there's going to be a little bit of light leakage. So that's why it's not great at detecting. Like right now, there's nothing in front of it, but it's still you can see there's some detection. There's something going on. I'll move this camera out of the way, but yeah, there's even though there's nothing in front of it, there's a little bit of a bump. But then as I move my hand close, you can see the signal does move. Now, something interesting that's happening is this line here. This is actually the response of the detector to the LED being on. But we actually see a bigger pulse over here, which is like the delta, the change in signal is much greater over here. This is where the LED is turned off. Now, why that might be happening, that diode, remember, is being biased and controlled by the decoder chip. That decoder chip, they don't really say what's going on, and other than they're like, well, there's automatic gain control and there's a bias circuit. What it might be doing is when it sees the signal go away, it might be increasing like the bias current to try to detect, like it might be tweaking the bias current to try to detect a signal that's disappearing, and so like kind of the signal overcompensates when it disappears. So what's interesting is in my code, so let's go to the copy. In my code here, I have it just stringing out the numbers. One thing I did is I made the analog resolution 12 bits. That's going to, on the CircuitPlayground, uses the AT7D processor. You get full 12 bits of analog if you ask for it. Otherwise, it gives you 10 bits. More bits, more better. So I upped it to 12 bit. Let's look at this serial plotter, because that's a little bit more handy. So this is it, just kind of, it's sitting, it's a little bit noisy. I'm not doing any averaging or anything. It's kind of, jumping around here, and then when I move my hand close, should be, it's moving, but it's like really hard to see. This is because, well, partially I'm reading it before the, you can see like the not the individual signal, but the average of the signal moves up and down. But this is because I'm measuring that signal at that little dip, not the big spike. So if I change this code around, actually, and let's go to the oscilloscope again, because I'll measure it. So I want to measure when, I want to measure it when it's right here, when it's kind of peaking right above it. So let's do cursor, and then I want to measure right after you turn it off. So I'll start the cursor at the off point, and then the other cursor, oh no man, what did I do? Whoops. The other cursor, I want to like measure it like right there. I want to measure it just as it peaks, and that says it is 36 microseconds. The thing is that it's hard to get actual microseconds. Wait, yeah, there's a delay for the analog read. Well, let's just say like delay microseconds 10, and then we'll move the proximity sense right behind it. Oh, can you pop back to the computer? Yeah, what I'll do is I'm just changing the code a little bit. Instead of doing the analog read as the LED is on, I'm going to do the analog read after the LED is off, and you get that little compensation spike. So let's re-upload it. While I'm uploading, are there any questions?
No, but how about I go to the overhead?
Mm-hmm.
And why don't you open up your mail real quick while we're doing this, and open up that link in another tab that I just sent you, just so you have it, so I can do my story later.
Okay, hold on.
It's called like.
I don't want people to see the garbage file. That's my email.
No, I know.
Okay.
They're not. Don't worry.
No, I know.
We're hiding your shame.
This one?
Yeah. There you go. Just
Oh,
keep
yeah,
that.
this
Just
is
keep
cool.
that in the tab.
Okay, I'm gonna close my email now.
Yeah.
Okay.
We'll get to that later.
Shh.
All right. What do you want to go to now?
Okay, so now that it's been uploaded, let's go back to the oscilloscope. So actually right now what's interesting is our pulse just got a lot smaller because we're no longer doing the analog read while the LED is on, which is actually kind of better for the LED anyway. So let's stretch this out. And then you can still see that there is, there is a little bit of a dip when the LED's on, but you get a much more pronounced reaction when the LED is off, when it's just turned off. So let's push this back here. Yeah, you can see it peaks up. So let's go to the serial plotter. And then I'll do the same thing. Hold on. Oh, you know what? I must not be taking enough time to read. Let's do, right, the pin is not connected. Right, you have to connect your signals. Okay, so let me connect my signal to A8. Sorry about that. Okay, so now, hold on, let me move this alligator clip out of the way. So now as I move my hand, I'm getting a range of about 1,800 to 3,000. So, there's some proximity sensing, if I'm in the middle here. I can do some averaging as well to smooth this out. Do you want to show the overhead?
Yeah.
So this is kind of the range. It's about it definitely is detecting as close as I can get, like 2 millimeters. And then the end of the range is about 3 to 4 inches away. And then, you can also use like something very reflective, like this white piece of paper. This is actually a little bit more effective. I can get up to like 5 inches away. Or maybe I'll do it this way. Oops, I think I broke it. Oh no. Oh well. I think I broke my circuit. So sad. Good timing, because I just finished up.
Okay.
Be careful with
Outside
alligator
a
clips.
mirror would work too.
A mirror, anything like that that's like white and reflective.
Yeah.
Let me see if this also just crashed. Hold on. Serial. No, I think I actually broke it. I think I touched the LED to ground by accident.
It's all right. You'll fix it. You always do.
Yeah, I could just solder on another one. Maybe I'll do that tomorrow's video. Yeah, I totally broke it because now I'm not getting any offset on my scope cam.
Yeah. Okay.
I got more LEDs though where that came from. Actually, I think I have another CircuitPlayground too. I could eventually bring it out. This is the risk and reward of live demos.
Yeah, sure, whatever.
Luckily, it broke right after the demo. So
You do what you had to do.
Yes. So the good news is, you can do proximity sensing. 3 inches is about the range, but it works pretty well. You can see you get nice spikes. This could be used for something like detecting when something's passing over it. Like if you want to detect something opening or moving without having to press the buttons. You can always have somebody press a button. Sometimes it's hard to align something if you're trying to measure or determine when something's moved. Getting it to line up with the button to press the button is a little challenging. So that's where a proximity sensor could be kind of handy. Probably a lot of other fun projects you can do with it. I like it as a neat extra hack. It doesn't cost me anything. I have an extra analog pin anyways. And so we wrapped up the silk screen. Oh, so can you go to the computer?
Yeah. So.
Are you bringing up my?
Yeah.
I know. It happens.
If I put it, you're now.
The Testing is actually when most things break, I found. You got like probes and wires everywhere. And these LEDs, they're a little delicate, like you can really overcurrent them and overdrive them if you're not careful.
Do you want to answer the question?
Yeah.
Any suggestions on how to use NeoPixel rings in fashion, and is this similar how they use lasers to calculate distance?
I actually don't know how distance laser works, but it's probably something similar. It's probably measuring some reflection. I know that we have the time of flight sensors. Those are really cool. They use little micro laser diodes. But I don't know exactly. I think those they're not detecting the amount of light, but actually the phase shift of the reflected light, which is different. Like they're actually measuring like the wavelength as it bounces back. There's a phase shift, and so they detect that, not the amplitude. This is actually just measuring, like literally, like you're shining a flashlight on it, and then you just see how much light is reflected back, and that tells you how far away it is.
Yeah, for NeoPixels in fashion, my suggestion would be to look at some of Sally Byer's projects, and also look on learn.adafruit.com, because we have a lot of NeoPixel in fashion projects. Okay.
Okay.
You want to wrap up?
Well, I thought I'd just show off this silk screen because this is the last thing. So, so given that I got the proximity sensing working, and I did get the PDM microphone working. I have to do more filtering on that. Maybe next week will be PDM filter party time. And then I basically wanted to redo the silk screen and get this ready. I thought maybe it would be nice to have these in the shop by Maker Faire. So doing a last prototype run so I could do like a final test jig, and then basically have to pull together all the code I've written into a CircuitPlayground library, something that people can use that makes it easy. And there's been a lot of hardware changes from the CircuitPlayground Classic, the Atmega 328 or 324 based version, to the SAMD version. We have a different kind of amplifier for the audio. We have analog output. Over here, I brought this pin out to do analog output. We have a digital microphone on the analog microphone. We have the IR receive, IR transmit. Same accelerometer. We've got that extra SPI flash, which is really neat. The thermistor and the light sensor are the same. But I think altogether, and then you got the proximity sense, which is part of this IR detector sender thing. There's a lot of little pieces that are new and extra. I also added like a fuse, for example, down here. Tried to like make this a little bit more durable. Never had a problem with not having a fuse, but whatever. It only costs a couple cents. Why not add it? So we redid the silk screen. So this is the new silk, and I like it. Phil B did this up. Did a really awesome job. Some things don't have pin numbers because, like, for example, the earphone, the microphone doesn't have a pin anymore. It's an I2S.
How much extra
microphone.
did the cost change make?
It's probably going to be about $5 more.
Okay.
Because of actually, it's more the complexity of the board. I'm a little concerned that the assembly and test procedure is going to be a lot longer. And also, there are more expensive parts. I think the actual individual parts cost is like $1 more in parts, but then the extra labor is going to add a little bit more than that, and then you have to multiply by 3. What's up?
What's the difference between the Dev Edition that we have and the Express? I can answer real quick.
Yeah, sure.
The Express is mostly going to be used for CircuitPython. You can run Arduino, but it's a more powerful next version of CircuitPlayground.
Yeah, I wanted to do kind of like a more advanced version. It has kind of everything that CircuitPlayground Classic has.
It's more advanced, but it's simpler to use.
Yeah, but it can run MicroPython.
Yeah.
And
our version, which is open source for CircuitPython, that's meant to just work with all of our hardware easily.
Also has things like analog output, which I think is really neat. It has that disk storage built in, which I think will be handy. Tony D wrote a great library for accessing that SPI flash as like a mini hard drive in Arduino, so you can use it for data logging or for storing like audio files and then playing them back out to the speaker or through this, or storing sensor data or LED light patterns. It also has like a ton more space.
Okay.
Much bigger processor.
Let's get out of here soon. Tony D's going to be streaming next.
Okay, great.
So just can you open up that tab? So I'll just tell people my infrared story because I'm old.
Okay.
So 13 years ago, I wrote a demo example how-to on Engadget back when gadget sites didn't have how-tos and Make Magazine didn't exist. Nothing like that. I think I started Hackaday shortly after. But what I did is I turned an iPod into a universal remote by recording the infrared sounds as sound files and then playing them back out through a sound to infrared converter. And you could tell how old this is by the iPod.
Yeah, that's cool.
Yeah, so just keep scrolling, and you could see kind of the gymnastics I need to do, and I wanted to show how anyone can do this without a lot of specialized hardware. I was using Pocket PCs. I was using this little sound to IR adapter.
Frugal.
Yeah, and there was a thing called Frugal back in the day. And basically, I did this before with Apple Newton, recording infrared signals, and then using sound, and then playing the sound through something that converts sound to IR. So you can see I did that in open source Audacity.
Now, what's funny is, of course, people who are listening in are probably saying, well, wait a minute, IR only does 44 kilohertz. IR is at 38 kilohertz carrier, and you're only sampling at 44 kilohertz. How does this work? Well, IR receivers are totally okay with a really, really, really shitty signal. Like you can be extremely abusive to an IR receiver in most devices, and they'll take it. Like they're totally cool with the frequency being off by like 50% or more. They're just looking for a change. They're looking for delta. They're not like that specific.
They didn't care.
They don't really care. Like, it's good to, if you get the best performance if you have that 38 kilohertz, but honestly, if you're down to 22 kilohertz.
Now, I got all sorts of hate. They're just like, this isn't the right way to do it. I'm like, it works. So it was a fun hack, and you could turn an iPod into a remote control. Completely pointless, lots of fun. And, turning off CNN 13 years ago was a good idea. It's still a good idea now. All right, so that's it.
Cool. Here's you can go to Radio Shack, get some parts. Let's see what happens if you click the Radio Shack link.
Yeah. Probably still works.
Nah.
Yeah. All right, that's the Desk of Ladyada tonight, everyone.
Okay.
Tony D's going to be doing a stream on Twitch. Check it out in a few minutes. Thank you so much, everyone. Thank you for making such a cool community. Thank you, everyone in the chat, for always making this fun. We'll keep doing streams over the weekend. We have Ask an Engineer next week, Show and Tell, all the usual things. We have a lot of fun stuff up ahead. And
digital filtering probably next week because I got to get this that microphone.
Yeah.
I got it working, but I have to getting good audio. Maybe we'll even record audio from the microphone on the CircuitPlayground Express and then play it back. That'd be cool. That's like a really good demo I want to do.
All right. Say good night, Ladyada.
Good night.
Good night and good luck.
Goodbye.